Hi, my name is Alex Salas, and today I will present the work titled Agent-Based Simulation of Hydroxyapatite Microcalcification Formation in a Three-Dimensional Macroenvironment. Hydroxyapatite microcalcifications are small mineral deposits that form in various human tissues. Their detection is highly relevant in biomedical fields as they serve as key biomarkers in tissues such as breast cancer and various kidney disorders. In breast cancer, microcalcifications are often visible in mammographic studies, and their detailed analysis helps differentiate between benign and malignant lesions. However, deposits their clinical importance. We still know little about the mechanisms behind their formations and ground most studies really in static imaging without offering a dynamic view in how these structures originate and evolve over time. The main goals was to develop a dynamic and flexible model that simulates the interactions of ions forming hydroxyapatite, thereby improving our understanding of nucleations, aggregation, and ground process. Hydroxyapatite has a chemical formula and consists of three main ions: calcium, phosphate, and hydroxyl. In our model, each ion was represented as an autonomous agent, capable of moving within a three-dimensional space. We defined a cubic macroenvironment where agents moved randomly, mimicking diffusive behavior in a liquid medium. When three different ions came within a critical distance, a new agent called microcalcification was formed. Additionally, we included a spontaneous nucleation parameter with a probability of 0.08, representing the possibility that under certain physiological conditions, crystals could be begin forming without strict ion proximity. The simulation was implemented in a Jupyter notebook and ran for 100 simulation days. The results aligned within physiological expectations and data reported in scientific literature. Number of classifications, we observed an almost linear increase over time, indicating sustained nucleations. Spatial distribution, microcalcifications were not uniformly distributed. Instead, clusters formed in certain regions. These patterns may reflect local macroenvironments more favorable to nucleations, such as high ion concentration or pH variations. Growth in average size. As the simulations progresses, microcalcification increases not only in number, but also in size. This behavior makes observation from electron microscopic in tissues and fluid samples. Together, these findings validate our model as a realistic representation of hydroxyapatite, microcalcifications, formations, and evolutions. This is the hydroxyapatite microcalcifications starts in day one and finish in day 100. In conclusion, this work demonstrates that agent-based simulation is an effective tool for studying complex biological phenomena like microcalcifications formations. The development model enabled us to represent ionic interactions forming hydroxyapatite, visualize the dynamic nucleations and ground process over 100 days, obtain results comparable to experimental data reported in the literature. Thank you very much for your attention.